This is the lab on hydrostatic pressure, and so here's the theory part, and this is the equipment for the experiment, but we did it a little different. We used something else. So here would be the bottle, and the bottle needs to be open. There's water in there. There's a hole right here, and water shoots out. You will see that in the video. And then we measure the distance, and we measure the water depth. We calculate what the velocity should be due to pressure. We calculate what the velocity really is with the kinematic equations from early in the class, and compare. And of course they should be the same, but why are they not? Okay, so and then here's a schematic of that. And again, I'm actually not using this kind of 2-liter bottle. We're actually using a tube, a long tube, 3 feet, 1 meter long, that is usually used for the speed of sound experiment, so I abused it for this particular one. Okay, here's the data table that you have to fill out. Again, I put the numbers that I actually measured in this particular font, so it looks like they're handwritten, so the data are already here. I still encourage you to watch the video though, because that one is just really quick. It took us less than a minute to actually film it because the water runs out very fast. We had to do really quick dynamic measurements. And that particular experiment is always quick. So the two in Unit 5, stress and strain, and this one here, hydrostatic pressure, they're always very quick. Besides doing these calculations, I will show you the example calculation in a moment. You also have to look up the orifice coefficient for the particular nozzle that we use, which is a nozzle that kind of shoots out. I really encourage you to Google orifice coefficient, and again, it's a little nozzle that goes outward. Here, I actually Googled it, and it kind of looks like this one here. So you have to imagine that this is the tube that the water is running out, and then this one is the nozzle towards the outside. All right, so here's the experiment, and I will do the example calculation after the experiment. Okay, now you can remove your finger. Okay, go ahead. And read off the 10 there. Oh, now. Okay, that's fine. That's fine, I got it. Okay, keep going. 120. Keep going. And now. 105. Okay. And now. It's 90. And one more. And now, that's 70, right? I think we got it. Good. So here's an example calculation so that you know how these formulas work. I'm not going to use the data that I supplied to you because there's so very few of them, so I want to save those for you. I'm just going to recreate my own example data from an experiment that I did years ago and put on here as an example. I also back then used the speed of sound tube, the clear plastic tube from that, and it has a square nozzle, so when you look up the orifice coefficient, look for something called a square nozzle or something close to that. Back then our drop height was 56 centimeters, so I'll be using that. Today it was different, and you saw it in the video, and respectively it's written on here as well. So I took these data out here. I'm gonna recreate these with the formulas. So the velocity due to pressure is 2 times gravity times height. So square root of 2 times 982 centimeters per second squared, because I measured in centimeters. So I'm not going to use 9.8. I'm going to use 982 centimeters per second squared. Times the depth of the fluid back then was 91.5 centimeters, parentheses, enter. And that rounds indeed to 424 centimeters per second. That's how fast it should come out. Apparently I'm using 3 sig fig here because I also measured with 3 sig fig. All right, then the other equation is the actual speed of efflux, so the speed with which it actually does come out. That should be the same, but we'll see in a moment. So that's the horizontal distance, which is 120, times the square root of, again, g is 982, divide by the denominator. I better put a parentheses around that. 2 times, and this one is the drop height, the 56 that you see down here. There we go. Close the parentheses for the denominator, close the parentheses for the square root, and I come up with 355. Oh yeah, that is because I used 120. I was supposed to use 70, my own. Okay, I'll fix that. So that's 7 here, and then I go back and delete this one here. Right there, 70. There we go. I fixed it. So it's actually around 210 centimeters per second. You saw that earlier, so appreciably less. So what happened here? Look up in the post lab. That's where I have an error calculation. Not an error calculation, but multiple choice question, multiple answer question about which kind of errors were involved here. And so look up for something, probably friction and the orifice itself, actually. So that's why I come up with something much lower. So if I take the 210 divided by the 424, I indeed come up with a rounded 0.50, 0.49 I had written earlier. Either way, 424, 210, 0.50 or 0.49. Either way, those two. Okay, and again, the analysis is actually straightforward, and the experiment also was really fast. If you had been able to do the experiment, you would have noticed that that was one of the fastest experiments.